Okay, in today's lecture, we're going to cover section 4.4 on tangent planes and linear approximations. So the problem that we're going to be considering in the first part of this section is the following. If we have a surface S, which is the graph of some function of two variables, f of x, y, then we can consider some point P, whose coordinates are x naught, y naught, z naught, on our surface. And we want to find the plane which would lie tangent to that surface at this point P. So one way that we can think about visualizing our tangent plane is by considering the following. If we were to look at vertical planes defined by x equals x naught, so for some fixed x value x naught, we consider a vertical plane passing through that value of x naught, we see that it would intersect our surface in a curve C2, which would pass through the point P, since the x-coordinate for our point P was x naught. And we could consider similarly a plane defined by y equals y naught. So the plane passing vertically through that y value would intersect our surface in this curve C1, which would also pass through the point P on our surface, since the y-coordinate for that point was y naught. Now we had seen that the partial derivatives of the function f evaluated at x naught, y naught, give us the slopes of these tangent lines T1 and T2 to our curves C1 and C2 at the point P. And we see that these two tangent lines define a plane, and this plane is what we define as the tangent plane to our surface. So our definition of the tangent plane is this plane defined by the tangent lines T1 and T2. Now, if we're interested in finding the equation of this plane, which we'll see could be used in some applications a little bit later in this section, we can make use of the following theorem. This theorem is the theorem for the equation of the tangent plane to a surface, defined as the graph of some function, f of xy, at a point x naught, y naught, z naught. So this theorem says the equation of that tangent plane is given by z minus z naught, which is then equal to the partial derivative of f with respect to x evaluated at the point x naught, y naught, times x minus x naught, plus the partial derivative of f with respect to y at the point x naught, y naught, times y minus y naught. And we're sometimes interested in solving this equation for the variable z. So here, if we were to solve for z, we would have z naught plus the partial derivative of f with respect to x, evaluated at x naught, y naught, times x minus x naught, plus the partial derivative of f with respect to y at x naught, y naught, times y minus y naught. And we'll see a little bit later in this section why we might be interested in solving for z in this case. So now that we have a way to find the equation of our tangent plane to a surface at a point, let's look at some examples of this. So in our first example, we are asked for the equation of the tangent plane to the surface z equals x squared minus 3y squared at the point -1, 1, -2. So this point that we're given is the point x naught, y naught, z naught when we think about our equation for the tangent plane. So there's a few things that we need to find in order to apply that equation. We have our point x naught, y naught, z naught. what we need to find are the partial derivatives of our function which defines the surface. So let's start by giving that function a name. In this case, we're looking at the surface z equals x squared minus 3y squared. So our function f of xy will be this x squared minus 3y squared. And then the partial derivatives of this function we need to find in order to make use of our theorem for the equation of this tangent plane. So we start with partial derivative of f with respect to x, which is 2x, and the partial derivative of f with respect to y is negative 6y. Now, if we look back at our equation, we need to evaluate those partial derivatives of f with respect to x at the point x naught, y naught, which in this case is the point negative 1, 1. So let's look at these partial derivatives at the point negative 1, 1. So our partial derivative with respect to x is negative 2, and partial derivative with respect to y at our point is negative 6. So now we're ready to make use of our theorem to find our equation. And the equation of this tangent plane is given by z minus z naught, which was negative 2. So we have z plus 2 is equal to our partial derivative of f with respect to x, which we found to be negative 2, times x minus x naught, which was negative 1. So we have x plus 1. And then we're adding the partial derivative of f with respect to y, which is negative 6, times y minus y naught, which was a positive 1. So we can simplify our equation a little bit. We've got then z plus 2 is equal to negative 2x minus 2 minus 6y plus 6. And we could either solve for z here by subtracting 2 from both sides, which would leave us z equals negative 2x minus 6y, plus 4 minus 2 would leave us a plus 2. Or if we preferred, we could write this in the standard form for the equation of a plane, which would be 2x plus 6y plus z is equal to 2. So depending on how we want to format our answer, we could either use this standard form for the equation of a plane or solve for a z. So let's look at some other examples of finding these equations of tangent planes. In our next example here, we've got the same sort of problem. Find the equation of the tangent plane to this surface at the point 1, 1, 1. So as in our last example, let's start by giving the function which defines this surface a name. Here, f of xy will be equal to e raised to the x minus y power. And we need to find our partial derivatives of this function. So here our partial derivative of f with respect to x is e to the x minus y power, and our partial derivative of f with respect to y, using the chain rule, is negative e to the x minus y power. So now we need to evaluate these partial derivatives at the point x naught, y naught, which in this problem is the point 1, 1. So here let's look at f sub x at 1, 1, which would be e to the 0, or 1, and the partial derivative of f with respect to y at the point 1, 1 is negative 1. So once we have these components, we're ready to apply our theorem for the equation of a tangent plane. And recall from our theorem that this equation is given by z minus z naught, which is 1, is equal to the partial derivative of f with respect to x, which we found to be 1, times x minus x naught, which is 1, plus the partial derivative of f with respect to y, which we found to be negative 1, times y minus y naught, and here y naught is 1. So if we simplify a little bit, we've got z minus 1 is equal to x minus 1 minus y plus 1. So here on this right-hand side, our plus minus 1 will cancel, and we can either solve for z, and we're left with x minus y plus 1, or if we prefer, we could express this in the standard form for the equation of a plane by moving all of our variables to one side. So we would have negative x plus y plus z is equal to 1. So either of these answers would work, depending on what format we prefer. All right, so in our next example, we have a very similar problem. Find the equation of a tangent plane to the following surface at the point 0, 0, 1. So again, let's start by giving this function which defines our surface a name. Here, f of xy will be defined as e to the x cosine of y. And if we find our partial derivatives of this function, we find the partial derivative with respect to x is e to the x cosine y, and the partial derivative of f with respect to y is negative e to the x sine of y. And we need to evaluate our partial derivatives at the point x naught, y naught, which in this example is the point 0, 0. So we find our partial derivative of f with respect to x at 0, 0 is 1, and our partial derivative of f with respect to y at 0, 0 is 0. So now we're ready to use the formula from our theorem for the equation of a tangent plane. And the equation of this plane is given by z minus z naught, which is 1. And that's equal to our partial derivative of f with respect to x, which we found to be 1, times x minus x naught, which was 0. Plus the partial derivative of f with respect to y, which we found to be 0, times y minus y naught, which was 0. So this last term disappears altogether since our partial derivative of f with respect to y was 0, and we're left with simply z minus 1 is equal to x. So solving for z, we would have x plus 1, or if we want to prefer to use that standard form for the equation of a plane, we could write this as negative x plus z is equal to 1. Again, either of these answers would be fine, just depending on what your preference is for how you want to express your answer. So in the next part of this section, we're going to talk about a linear approximation. And really, a linear approximation is just the equation of the tangent plane to a surface. And we'll see that we can use our tangent plane to approximate values of a function near a point, which may not be very easy to evaluate, say, without the use of a calculator. So in this next part of our section, let's start by defining a linear approximation. So here, the linear approximation, or sometimes called linearization, of a function f of xy at a point x naught, y naught, is defined to be the equation of the tangent plane to that surface defined by our function f of xy at the point x naught, y naught. So here, the linearization is this function, which we will denote as capital L for linearization, and it is defined as f of x naught, y naught. Now, f of x naught y naught, this is really just the z naught coordinate for our point, because our surface that we're considering is defined by z equals f of xy. So if we evaluate f at this point x naught y naught, we get the z coordinate for a point on our surface, z naught. And then the remainder of our equation for this linearization is the partial derivative of f with respect to x at x naught y naught times x minus x naught, plus the partial derivative of f with respect to y at x naught y naught times y minus y naught. So we recognize this as just the equation of the tangent plane to our surface at the point x naught y naught. It's the same problem that we were working with in the first part of this section. So recall that anytime you are asked to find a linearization or linear approximation of a function at a point, the problem is really just asking you to find the equation of your tangent plane, and this linearization is then denoted as capital L. So let's look at an example of finding a linearization, and then how we could use it to approximate the value of a function. So in this next example, we are asked for the linearization of the function x squared plus y squared plus sine of xy at the point 0, 2. So this point 0, 2 is our point x naught y naught. And in this example, we were not given our z naught coordinate. So to find z naught, we're going to evaluate our function f at the point x naught y naught, which was 0, 2. And we find that this value is 4. So now, from here, the problem is just like the examples we were considering earlier, where we're trying to find the equation of our tangent plane. So let's start by finding the partial derivatives of our function f with respect to x and y. So here we find our partial derivative of f with respect to x is 2x, plus, using the chain rule, we have cosine of x times y times the derivative of the inner function with respect to x, which would leave us a factor of y out in front, and the partial derivative of f with respect to y is given by 2y plus x times cosine of xy. Again, we're using the chain rule to find our derivative of that sine of xy term. So now evaluating these partial derivatives at our point x naught y naught, in this case 0, 2, we have our partial derivative with respect to x is 2, and partial derivative with respect to y at the point 0, 2 leaves us 4. So now to find our linearization, well, we're just going to find the equation of our tangent plane, the same as what we were doing previously. So here, the equation of our tangent plane would be z minus z naught, which is 4. And that's equal to the partial derivative with respect to x, which we found as 2, times x minus x naught, which was 0, plus the partial derivative of f with respect to y, which we found to be 4, times y minus y naught, which was 2. So now solving for z, we have z is equal to 4 plus 2 times x minus 0, or just 2x, plus 4y minus 8. And simplifying, we're left with z equals 2x plus 4y minus 4. Or in this problem, we were asked for a linearization. So rather than thinking about this as the tangent plane, we might use the notation capital L of xy, thinking about this linearization as a function, and it would be the function 2x plus 4y minus 4. So here we've got the following function as our linearization. Now, we might be wondering, well, what good is this linearization? Why do we care about finding the equation of a tangent plane to a surface at some point? And the reason is that we can use the equation of a tangent plane to approximate the values of our function near the point x naught, y naught, where we were approximating. So we can think about that geometrically. If we go back to the equation or the graph of our surface and our plane, and we can see that if we were to consider points near the point x naught, y naught in the domain of our function, so let's choose some other point nearby, say here, and we were to look at the value of our function at that point by plugging this point into our function, we see that we could use a point on the tangent plane evaluated at x naught, y naught, and it would be approximately the value of our function f at this point close to x naught, y naught. So in this next example we're going to consider, we will find a linear approximation of a function at the point 0, 0, and then we're asked to use this to approximate the value of the function f at negative 0.1, 0.2. So in the first part of this problem, as with our previous example, we need to start by finding our z naught coordinate. So here, z naught is given by the value of our function f at the point x naught, y naught, which we were given as 0, 0. And we find that this z naught coordinate is sine of 0 or 0. So now, from here, we need to find the partial derivatives of our function. So here, partial of f with respect to x, using the chain rule, is given by cosine of x plus 2y times the derivative of the inside with respect to x, which is just 1. And the partial derivative of f with respect to y is 2 times cosine of x plus 2y, again making use of the chain rule there. So if we evaluate our partial derivatives at the point 0, 0, we find our partial with respect to x is 1, and partial with respect to y at 0, 0 is 2. So now, making use of our equation for the tangent plane to a surface, we find the tangent plane is given by z minus z naught, which was 0, and that's equal to our partial with respect to x, which we found to be 1, times x minus x naught, which was 0, plus the partial of f with respect to y, which we found to be 2, times y minus y naught, which was 0. So here we have immediately our solution for z, and we might call this linearization capital L of xy, and in simplified form we just have x plus 2y. So this would be the linearization of our function at the point 0, 0, and we are asked to use this linearization to approximate the value of our function at this point, negative 0.1, 0.2. So if we wanted to use this function, or our linearization to approximate this function at the indicated point, we could simply plug this point, negative 0.1, 0.2, into our linearization, and we get x plus 2y, which in this case is negative 0.1, plus 2 times 0.2, or 0.4, and we're left with 0.3. So this value that we get by substituting into our linearization is an approximation of the value of our function at that point. Now, why might we need to use the linearization to approximate this function? Well, let's look at the left-hand side of this equation. If we were to plug our point directly into our function, it's a little messy. We have a sine of x plus 2y, which is 0.3, and it's difficult to evaluate sine of 0.3 without the use of a calculator. But through this linearization, we find that this value is approximately 0.3. And if we check that with the calculator, we see it's, in fact, a very good approximation. Now, in the last part of our section, we're going to introduce the concept of differentials for multivariable functions. Now, you might recall working with differentials a lot in your Calculus 2 class. For instance, if we have some function, say y equals f of x, then we would define the differential dy to be f prime of x times the differential of x. So these differentials dy or dx usually represent a very small change or a very small quantity in, say, the x or the y direction. So dx would be a small length in the along the x-axis, and dy would be a small length along the y-axis, or a small change in the quantities x or y. So we've got this definition of differentials for single variable functions. So let's consider these for multivariable functions. For instance, if we have z equals f of xy, then we could define the differential of z to be dz, and it's defined as the sum of our partial derivatives of f with respect to x and y times the respective differentials dx or dy. And similarly, if we were looking at a function of 3 variables, say w equals f of x, y, z, then we could define the differential, or sometimes called a total differential, of w as dw is equal to, again, the sum of our partial derivatives of f with respect to x, y, and z, each multiplied by the respective differentials dx, dy, or dz. So, of course, we could extend this definition if we were interested in finding differentials of functions of 4 or more variables, but in our course, we typically only work with functions of 2 or 3 variables. So let's look at some examples of finding differentials of these multivariable functions. So in this first example, part A, we have z defined as 3y times cosine of x times y. So this is a function of 2 variables, x and y. So our differential, or total differential of z, which we denote as dz, would be given by the partial derivative of f with respect to x times the differential of x plus the partial derivative of f with respect to y times the differential of y. So really all we need to find are the partial derivatives of this function. So here we have dz is equal to our partial derivative with respect to x. So here we have a constant 3y out in front, and using the chain rule to differentiate cosine of x times y, we have a negative sine of x times y times the derivative of the inner function with respect to x, which would be y. So we have another factor of y out in front, which gives us a y squared. So altogether, negative 3y squared times sine of xy. And then we're multiplying that partial derivative by the differential of x dx. And then we would add the partial derivative of f with respect to y. So here, looking at our function, we see that this partial derivative is a little trickier. We've got to make use of the product and chain rules. So differentiating our first factor, 3y, with respect to y, we have 3. And then we multiply by the second factor, cosine of xy. And then we add our second factor, which is 3y, times the derivative of cosine of xy with respect to y. So making use of the chain rule, we have a negative x times sine of xy. And then we are multiplying this partial derivative by the differential of y, or dy. So simplifying a little bit, we have dz is negative 3y squared sine of xy dx plus 3 cosine of xy minus 3y, or 3xy, sine of xy, all times dy. So this would be our differential, or total differential, of this quantity z. Now, we had mentioned that the differentials dx and dy represent small changes in the variable x or y. So this differential that we're finding, dz, is denoting a small change in the z variable. And we can see here, because z is a function of x and y, that this change in the z direction would be defined by the following. And we're going to see why, or where we could use these differentials in some applications at the last part of this section. So in our next example, we have a function w, which is 2xy times e to the xz. So this is a function of 3 variables, f of x, y, and z. And we are asked to find the differential, or total differential. So in this case, for a 3-variable function, we would have our differential dw defined as the partial derivative of f with respect to x times the differential of x plus the partial derivative of f with respect to y times the differential of y plus the partial derivative of f with respect to z times the differential of z. So in this case, let's see what we have. Our differential dw is, well, differentiating with respect to x, we're going to make use of the product and chain rules. So differentiating 2xy with respect to x, we have 2y times our second factor in the product, which is e to the xz, plus our first factor, 2xy, and the derivative of e to the xz gives us e to the xz times the derivative of the inner function with respect to x, which leaves us z. So altogether 2xyz times e to the xz power, and we multiply by the differential dx. Then we add f sub y, or our partial derivative with respect to y, is 2x e to the xz times the differential of y, and then we add our partial derivative of f with respect to z, which, making use of the chain rule, gives us 2x squared y e to the xz times the differential of z. So this would be our total differential for that 3-variable function. Okay. Now in the last couple of examples that we will consider in this section, we'll look at some applications of differentials in determining, say, the error that would occur in some quantity if we had small errors in measurement. So as an example of this, let's consider the following. We have the base radius and height of a right circular cone are measured as 10 centimeters and 25 centimeters respectively. And we are told that there is a possible error in measurement of at most 0.1 centimeters in each of those quantities. So we are then asked to use differentials to estimate the maximum possible error in the calculated volume of this cone. So here, let's visualize our situation. We have a right circular cone. I'll draw it inverted here. And it has a base radius that we will call r, and a height, which I'll call h. We are told that the quantities r and h were measured to be 10 centimeters and 25 centimeters for these measurements. And we're told that there's a possible error in measurement of at most 0.1 centimeter in each of these quantities. So there could be some small change in the true height or true radius of this cone. And these small errors or small changes in the values of r or h, we could think of as differentials, small changes in r, the radius of our cone, or h. So we could consider the differential of r or the differential of h, and we were told that these are at most 0.1 centimeters. So these differentials would have to be less than or equal to 0.1 centimeters each. And now we are asked to determine, well, for these possible errors in measurement, what is the maximum error in the calculated volume of our cone? So we're asking here about the volume of this cone. I'll denote it as V. And the volume of a right circular cone is given by 1/3 pi times r squared, the radius squared, times the height of our cone. So we are looking for a small error or a possible error in the volume of this cone, which we could think of as the differential of this volume function. Now here our volume we see is a function of two variables. We can think about this v function as depending on the radius and height of our cone. So we're really asking about a total differential of this volume function. So to find this, we know we would first look at the partial derivative of volume with respect to the first variable, which we're calling r, times the differential of r, plus the volume of our cone, its partial derivative with respect to height, times the differential of height. So let's evaluate these partial derivatives. We have dv is equal to our partial derivative with respect to r is 2/3 pi r times h, and then we're multiplying this by the differential of r. And our partial derivative with respect to h is 1/3 pi r squared times our differential dh. Now, if we want to know the largest possible value in this differential, or our largest possible error, we want to maximize this differential, dv. So we know that the largest possible value it could take would be when we see the largest possible errors in our measured radius or height. That is, our largest values for dr or dh, which we found to be 0.1 centimeters each. and then the values for R and H that we had measured were 10 and 25 centimeters respectively. So let's evaluate this expression that we found for our differential at these quantities which we've measured. We have 2/3 pi times R, which was 10, times H, which was 25, times the differential of R, which had a maximum value of 0.1 centimeters. And then we are adding 1/3 pi times R squared. So we have 10 squared, or 100, times the differential of H, which is at maximum 0.1. So here, let's simplify a little bit. We have dV is less than or equal to, well, here our 10 and 1/10 cancel. Here we have a 100 times 1/10, which reduces to 10. So we are left with, for this first part, a 50 pi over 3 plus 10 pi over 3. So we have 60 pi over 3, or a maximum possible error in volume of 20 pi. And since we were measuring everything in terms of centimeters, this volume would then be cubic centimeters. So we see in this case that even though we had relatively small errors in measurement for the radius and the height, 0.1 centimeters in either case, it could result in a maximum possible error in the volume of 20 pi cubic centimeters, so 60 cubic centimeters and some change. So possibly a relatively large error in the volume, despite those small measurement errors in the radius or the height. So in our last example, we've got a problem that's pretty similar to this previous one. We're told that the dimensions of a closed rectangular box are measured as 99 centimeters, 53 centimeters, and 40 centimeters. And we have a possible error of 0.2 in each dimension. So we want to use differentials to estimate the maximum error in the surface area for this box. So let's again visualize our setup here. We have some rectangular box, and the dimensions of this box we will denote as X, Y, and Z. And we are told that these dimensions were measured as 99 centimeters, 53 centimeters, and 40 centimeters. And we had a possible error of 0.2 centimeters in each of these dimensions. So the differentials for X, Y, and Z would be at most 0.2. So now we are asked about the maximum error in the surface area of this box based off those measurements. So let's think about how to find our surface area. We'll call this function S for surface area. And we were told it was a closed rectangular box in the problem statement. So it has a top. So the surface area of this box would be found by adding the area of all of our sides. So the top and the bottom of this box are both of area X times Y. And we have the top and the bottom, so adding those, we'll have 2 times XY. Now then, if we consider the front and back of the box, so when I'm saying the front, I'm referring to this shaded side here, and we see that its area would be X times Z. So since we have the front and the back of our box, we'll have 2 times XZ, And then we have to add the area of our left and right hand sides. So for, say, this right hand side of our box, we see that its area would be y times z. And we have the left and the right hand side, so we have two sides of area y times z. So our surface area function is a function of three variables, x, y, and z, and we are asked about the differential or possible error in this quantity. So let's look for our total differential ds. So here we start by looking at our partial derivative with respect to x, which would be 2y plus 2z times the differential of x, plus our partial derivative with respect to y, which is 2x plus 2z times dy, and then plus the partial derivative with respect to z. So we're going to have 2x plus 2y times the differential of z. So to determine the maximum possible error in calculating our surface area, we want to maximize this differential. And to do that, we would be looking at what the maximum errors would be in measuring each of our dimensions. So here, if we substitute our values for x, y, and z, along with these maximum values for the differentials into the expression we just found, well, we have 2 times y plus z, so 53 plus 40, times the differential dx, which was at most 0.2, plus for this next term, we can factor out our 2. We have x plus z, or 99 plus 40, times the differential of y, which was at most 0.2. And then for our last quantity, we have 2 times x plus y, which would be 99 plus 53, times our maximum value for the differential of z, which was 0.2. So if we simplify this quantity, we end up with the maximum value for this differential as 153.6. And since we're talking about area here, we were measuring in centimeters, area would then be in square centimeters. So again, we see even for a pretty small error in each dimension, we could have a relatively large error for calculating some related quantity like the surface area of our box.